So, what we're going to start in on today is a general area of integration techniques that together go by the name of trigonometric substitution. And sometimes you will see this also known as inverse substitution because it's it's not exactly an inverse substitution, okay? It's really just kind of like another substitution. But normally we have a function inside of our integral and we make a new variable equal to that function. Well, this is sort of the inverse of that because instead of kind of making a new variable equal to our function, we're going to take our original variable and set it equal to a new function. So in that sense, this is a little bit weird or different than our usual substitutions, but it really is just the same kind of idea. And I want to show you where this kind of thing comes up, and we'll see in a sort of hopefully somewhat natural way why you want to do this and why it works. And then we'll kind of go through a bunch of different examples and see in general, like here's a bunch of different techniques. But here's just a basic example where trig substitution comes into play and where, yeah, it's really important. So let's take a look at the integral of square root 1 minus x squared divided by x, and then the whole square root is divided by x squared dx. There we go. Okay, so we want to try to do this integral. Now, I can't do a substitution, not like a direct substitution of the kind we usually would like to try. I also cannot, as I look at this, it doesn't really look like doing integration by parts is going to do much for me either, honestly. It's just going to kind of continue creating a mess with this square root staying in here. So what am I going to do? Well, here's the thing that you want to recognize. It would be way, way easier if we didn't have multiple terms inside the square root. If we could somehow get this down to just a simple power of something, even if it's a fractional power or whatever, it would just be a lot easier if we could do something like that and kind of get rid of that. Maybe we could even get rid of the square root entirely. And what you want to remember is that things of the form 1 minus something squared, that shows up in the Pythagorean identity. And that is sort of the key observation behind all of trigonometric substitutions. The key observation is that if we replace x, or whatever variable we're using, in this case x, but if we replace this with a trig function, we can use the Pythagorean identities. Remember, on the one hand, there's kind of one Pythagorean identity. It's sine squared plus cosine squared equals 1. On the other hand, there's actually 3 different forms of that because I can turn that into an identity for tangents and secants, and I can also turn that into an identity for cotangents and cosecants. So there's really 3 different Pythagorean identities, even though they are all equivalent to each other. But that's the real purpose behind trig substitution. If we could write something out in terms of trig functions, then we get to use the Pythagorean identities, and if we get to use the Pythagorean identities, that might help us to simplify things that look like, for instance, 1 minus x squared. So we might try just seeing, well, what would happen if I rewrote this thing in terms of trig functions? How would I go about doing that? Well, let's just try sort of the almost naive thing to do if we want to try rewriting this in terms of trig functions. Let's just say, okay, what I would like to make use of is the fact that 1 minus sine squared theta is cosine squared theta because I have 1 minus something squared. And therefore, what I would like to do is to set x equal to the sine of theta. Now, if I do that, and I can do that, but I have to be careful when I do to make sure that everything works out correctly. I have to make sure that I substitute everything just right. then dx is going to actually be equal to cosine theta d theta. So I take the derivative of this with respect to theta and I multiply it by d theta. Remember, that's how differentials work. You take the derivative and you tack on d whatever variable. So now what I'm going to do is see what happens when I rewrite this original integral in terms of these new, in terms of this new variable theta, but in particular, that means I'm going to rewrite everything in terms of trig functions of this new variable. So I'm going to have the integral of, let's see, the square root of 1 minus sine squared theta. That's kind of the whole reason I did this. And then in the denominator, I will have sine squared theta. And then dx is cosine theta d theta. So let's watch what happens now, because this turns into the integral of cosine squared theta divided by sine squared theta times cosine theta d theta. And this just becomes, when I simplify it, this is going to become the integral of cos squared theta over sine squared theta d theta. If I disregard for the moment that square root cosine squared is actually positive cosine theta, and there is a reason why I can do this. The reason is because this really means that theta is equal to sine inverse of x. However, sine inverse of x has a range from minus pi over 2 to positive pi over 2, and on that interval, cosine theta is always positive. So technically, this in the numerator here, this is the absolute value of cosine theta, but with the range that we're thinking of theta here, we can just say, well, that's the same as cosine theta because the cosine is positive here. That's sort of a technical note that I wanted to mention here, but don't think too much about, don't worry too much about that the first time you look through this. The second time or third time you look through this, then maybe think about why is it that I can get rid of the absolute value. But for the first time, just notice that naively we can kind of get this into a cosine squared. And then what do we do? Well, this is actually the integral of cotangent squared theta d theta. Now, we haven't looked exactly at an integral that looks just like this before, but it's actually not too bad to do. And let me explain why, but I'm going to have to erase some stuff here. So I want to leave this stuff alone, so I'm going to just erase the line above it. You see, what we can do is we can make use of a Pythagorean identity again. I can say that the cotangent squared, this is actually the integral of cosecant squared theta minus 1 d theta. Now, why do I want to do that? Well, because I know what the antiderivative of cosecant squared is. Why do I know that? The derivative of cotangent is negative cosecant squared. So this is going to become negative cotangent theta minus theta plus a constant. So now I have my antiderivative actually calculated. It's just that it's written out in terms of theta. And so what we would like to do now is we would like to rewrite this in terms of x's, which was our original variable. Now, the theta itself, all we can say here is that theta is sine inverse of x. So that's just going to become a minus sine inverse of x. But what about the cotangent of theta? This is actually the cotangent of the inverse sine of x. But there's a little trick that we can do for these. And you might remember this from pre-calculus. Maybe when I show you the trick anyway, you'll start remembering it. So what I can do is I can say, if x is equal to the sine of theta, let's think about a triangle, a right triangle, that has x being equal to the sine of theta. So I'm going to create an angle here, theta, in this right triangle. If x is the sine of theta, then if I make this side x and this side 1, x is, in fact, the sine of theta. And then what I can do is I can ask, okay, so what is the cotangent of this angle? Well, the cotangent is adjacent divided by opposite. And adjacent divided by opposite in this case is square root 1 minus x squared. Now, how did I get this? Well, I just used the Pythagorean theorem to complete this triangle's dimensions. Hopefully everybody remembers how to use the Pythagorean theorem and everything to complete a triangle like this. We're using Pythagorean identities a lot, and this is kind of the same idea. So what we can say then is that this is negative cotangent theta, but the cotangent is the adjacent over the opposite. So this is negative square root 1 minus x squared divided by x, because that's the opposite side. And then we have to subtract sine inverse of x, and we add on our constant of integration, which for some reason I've been using k a lot for my constant of integration instead of c, but it doesn't really matter. I think your homework system likes you to use a c. But for some reason, I keep switching this to a K, and I'm not going to go back and redo this with a C. I guess we could just erase this and put in C's if we want. So there we go. Everything is now in terms of C's. Now, that seems complicated, right? And I'm not going to lie to you here. It's a complicated process. A lot of students find this trigonometric substitution stuff to be very, very challenging. And my goal here is to explain it to you in a way that hopefully will make it sort of not as horrible and challenging, because if you understand where it comes from, then it helps you to do it. And so again, I want to say the reason that we think of doing this is because we see something in the original, in this case a 1 minus x squared, and we think to ourselves, that looks an awful lot like something we see in a Pythagorean identity. If this x were just a trig function of some kind, then, well, we'd be able to use a Pythagorean identity and things would simplify. So whenever you see something in your integral that looks like it would simplify if only you could use a Pythagorean identity, the idea behind trig substitution is, let's just make it so. Let's do a substitution where let me start that over. We do a substitution where our old variable x is equal to a trig function of our new variable, the goal being to be able to use the Pythagorean identity to simplify this thing. Now, what if it weren't quite this straightforward? For instance, what if instead of having this as my original integral, I had something a bit more complicated? So let me suppose that I do almost the same integral, but let's say that I have the integral of the square root of 9 minus 4x squared divided by x squared dx. So the problem here that we encounter is in this integral, I no longer have something quite so straightforward. I no longer just have 1 minus x squared. However, naively, we might hope that we can sort of do the same thing again in some sort of a way. And it turns out that, yes, there is a trick to this. And I want to explain where the trick comes from. The key is I want to rewrite this as the square root of 9 times 1 minus, what is this going to be? Well, actually, first of all, let me rewrite it like this. Let's write this as 3 squared minus 2 squared x squared. And then, I'm only rewriting this square root here for the moment, by the way. I'm just going to show you how I can rewrite the inside. Because what I would like to do is I would like to get this up to 1 minus something squared. And so what I can now do is I can rewrite this as the square root of 3 squared minus 3 squared times 2 squared over 3 squared x squared. And then I can bring out this 3 squared, and I can rewrite this as 3 times the square root of 1 minus 2/3 x squared. Now, this is not exactly the same as what we had, or if I wanted to, I could even write this differently. I could leave the 3 squared inside the square root. Anyway, this is not exactly what we had, but let's kind of rewrite the integral in these terms. So we have 3 times the square root of 1 minus 2/3 x squared, all divided by x squared. Now, what I'm going to do, and I'm going to have to erase this in order to do it, but what I'm going to do is I'm now going to say, okay, if 2/3 x were a trig function, this could be handled with the Pythagorean identity, right? Exactly like we handled the last one. So I'm just going to say, let's let 2/3 x be equal to sine theta. Then dx, well, one thing we can say is that x is 3/2 sine theta. Dx is going to be, whoops, I lost my dx up here. This is going to be 3/2 cosine theta d theta. Okay, and then what does this whole integral become? Well, the integral is going to become, and we need to keep track of all of this stuff because we have a lot of stuff floating around here, but we have 3. Then we have the square root of 1 minus sine squared theta. Then we have times 3/2 cosine theta d theta. That comes from the dx. And then x squared, this is going to be 9/4 sine squared theta. But you'll notice that at this point, we're pretty much back where we were in the other integral, okay? We've almost got everything worked out in exactly the same way, because at this point, I can do the same simplifications. I can once again say that this is going to just become cosine theta. So we're going to have a cosine squared theta over a sine squared theta. The only thing is we have 9/2 over 9/4, so we're going to end up with an extra factor of 2. So let's go ahead and do that. And I'm going to have to erase the original thing here, but let me leave the substitution that we did. So 3 times 3, that's 9/2. 9/2 divided by 9/4 is going to be right, so just to remind you how this works, 9/2 times 4 over 9, and this comes out to be 2, right? So just in case you were having trouble seeing where those fractions came from, this comes out to be 2. So this is going to become 2 times the integral of cosine squared theta over sine squared theta d theta. And once again, here's what I can do with this. I can now take this and I can say, and I want to leave this substitution up. In fact, let's write the substitution that we had up here so that I can keep it in a corner. 2/3 x equals sine theta. And then x equals 3/2 sine theta. And we'll lead that in a minute here. But to do this integral, well, we already did this integral, so I'm going to go through it kind of quick this time. We're going to have 2 times the integral of cotangent squared theta d theta. This is going to be 2 times the integral of cosecant squared theta minus 1 d theta. Once again, Pythagorean identity stuff. This is going to become -2 cot theta minus 2 theta plus c. What is cotangent theta, though? Well, to figure out cotangent theta, I can make another triangle here. So I can say, on the one hand, from this, what we can see is that theta is equal to sine inverse of 2/3 x. But on the other hand, what we can say is that if I just build a triangle here with an angle of theta, then if the hypotenuse is 1, this side will be 2/3 x, and now sine of theta will be 2/3 x. The adjacent side is therefore going to be the square root of 1 minus 4x squared over 9. So the cotangent is once again the adjacent over the opposite. So this is going to be negative 2 times square root 1 minus 4x squared over 9, all divided by 2/3 x plus theta plus a constant. And then, of course, you can go ahead. I will leave it to you to simplify those fractions at this point. It's a very simple exercise to cancel stuff if you want to. Or, we flip this around so that this is actually 3 halves, multiplying this fraction, however you want to simplify that. So as you can see, we were able to do the same trick. Even though we didn't start with something that looks like 1 minus x squared, we were still able to do the same trick. And in fact, if you think about it for a minute, this is going to be possible in general anytime that I see something that looks like this. If I have the square root of a squared minus b squared x squared, if I want to try to do a simplification with this, what I can do is I can always think of this as the square root of a squared times 1 minus b squared over a squared x, or x squared. And this is going to be a times the square root of 1 minus bx over a squared. There we go. Sorry, just double checking to make sure that I am not lying to you here, that I'm doing everything correctly. So what we can do at this point is we substitute x is equal to, b over a times x is equal to sine theta. So I take this quantity here, I set it equal to sine theta, and that is my new variable. And when I do that, I want to emphasize here, that is going to fix up my problem for me. At least that's the hope. Now, I'm not going to tell you this will work literally every single time, but the hope is that if you do this, at the very least, it will allow you to simplify this kind of square root situation. You can use this in situations where you don't even have a square root, maybe. Maybe you've got some other kind of expression, but it has an a squared minus b squared x squared. And for some reason, you want to consolidate this into one piece. Well, yeah, you can go ahead and you can try to do that if you want to. Why not? You can use this same technique. If for some reason you just need to simplify a squared minus b squared x squared. However, in more situations than not, probably, if you just have the a squared minus b squared x squared by itself with no square roots over or anything, then maybe there's another way to do it that doesn't require this trig substitution. So usually we always think of this when we see square roots of this kind. Give me 1 second here. Okay, so I was just making sure that this really is a good example for this. So what I would like for you guys to do is pause this video for a minute and see if you can use the same kinds of ideas to work on this problem. See if you can work this out. I actually think in some ways this one might work out a little bit neater than the example we started with. So again, take a few minutes, and these are lengthy problems, so I do encourage you to really take a few minutes to think about this and see what you are able to come up with. Okay, were you able to see anything with this? So here's the way that I would think about this problem. I'm going to look at this and I'm going to say, well, this is the same thing as the integral of x over 4 times the square root of 1 minus 5 over 4x squared dx. And now what do I want to do? Well, I want to set 5 over 4x equal to sine theta. That means that dx is going to be equal to 4 over 5 cosine theta d theta. That's really kind of squeezed in there. Let me try to write that a little bit more legibly. I don't know how much that helps, but hopefully you can see what's going on there. And then what am I going to do? Well, I'm going to rewrite this whole thing the same way as we would before. So x is actually 4/5 sine theta. And then dx gives me another 4 over 5 and a cosine theta. And in the denominator here, I still have a 4, and then I have the square root of 1 minus sine squared theta. And the whole thing has a d theta on it. Now, one thing I can do right off the bat is I can cancel one of my 4's in the numerator with that 4 in the denominator. And, you know, is it essential to do that? Well, no, but frankly, I'd like to get these fractions as simple as possible because this is messy enough as it is. I don't need to make things even messier on myself. So then what am I going to do? Well, this is going to become the integral of, now we're going to have 4 over 25. So I'm just consolidating all of these constants out front for the moment. That doesn't look much like a 4. That's a bit better of a 4. Okay, so then I have sine theta, cosine theta, divided by cosine theta, d theta. My cosine thetas cancel. The antiderivative of sine is negative cosine, and we end up with negative 4 over 25 cosine theta plus a constant. So as I told you, this actually works out a little bit neater than the previous example. Of course, we're not done yet. This is not quite the end of the problem, because I now have to go back and plug in everything in terms of x's. Now, you could say, well, theta is the inverse sine of 5/4 x, so we're taking cosine of inverse sine. But what is a cosine of an inverse sine? It's, again, something we can work out using a triangle. And the triangle that we're going to build here is we are going to set up a triangle, hypotenuse 1 and opposite side of 5 over 4x. And then cosine is just adjacent over hypotenuse. So the adjacent side, in this case, is the square root of 1 minus 25 over 16 x squared. So my integral here is actually going to be negative 4 over 25 times the square root of 1 minus 25 over 16 x squared plus a constant. I suppose if you really wanted to, you could then bring this 4 over 25 inside the square root and simplify some stuff in there. I don't personally feel like that's all that essential or anything, but you could do it if you wanted to, just mess around with the properties of square roots. But we've got everything back in terms of x's, so there we go. All right, now we've only looked at some examples here involving sines. Now here's the thing. There's actually 2 more forms of the Pythagorean identity that are really worth considering. And to show you how those identities can come up, I want to think about another example that looks a little bit different than what we have. So let me pull that up. All right, I've got my next example ready to go here. I just want to make sure that I actually am showing you the right thing, because like I said, these are not easy problems. I need to make sure that I'm doing these correctly too. I don't want to spend a bunch of time staring at it being like, wait a second, did I do this? Am I making sure that I'm doing this correctly? So let's suppose that I want to do this. Let's suppose that I want to do the integral of dx divided by x squared times the square root of x squared plus 4. Now, how would I end up doing this? Well, I cannot use the sign substitution that we just did, right? That's not going to work. But what I might notice here is there is a nice identity. Tangent squared theta plus 1 is secant squared theta. So maybe there's a way that I can mess around with this and get it to help me out here. Well, there is, because think about what this looks like. This is actually going to be the integral of dx divided by 2x squared times the square root of, and now we got to make sure that we do this exactly correctly. This is going to be x over 2 squared plus 1. Take a minute to make sure you see how I did this. I factored a 4 out of each of these terms, and then I brought that 4 outside of the square root. And then I have x squared over 4, which is really x over 2 squared. Now, the thing is, at this point, what I have on the inside is some fraction squared plus 1. And I can go ahead and say, well, if that fraction were actually the tangent of theta, this would all work out beautifully for me. I could use this Pythagorean identity here. So let's go ahead and try it out. It's going to be the same kind of thing as we did before, except instead of using sines and cosines, we're using tangents and secants. Now, is that a little bit messier? Yeah, it's slightly messier in some ways, but honestly, it's not that much different. And depending on the problem, as we'll see, this problem is going to turn into something that's not so horrible compared to what we've been doing before. So let's say that x over 2 equals tangent theta. That means x equals 2 tangent theta. That means that dx is, remember the derivative of tangent? Because you're going to need that a lot. It's going to be secant squared theta d theta. Wait, I lost the 2. It's going to be 2 secant squared theta d theta. There we go. My 2 is back where it belongs. Okay. Now what can we do? Well, let's see what that allows us to do with simplifying this problem, and then we'll worry about whether we can do the resulting integral. Hopefully we'll be able to find a way to do that. So we're going to rewrite this, and we're going to have to do this. There is going to be a little bit of a period here where things are messy. So we're going to have 2 secant squared theta d theta. That's from my dx in the numerator. Now, in the denominator, we're going to have a tremendous amount of stuff. We're going to have 2. Then we have 2 tan theta squared. So that's going to be times 4 tangent squared theta. Then I have the square root of tan squared theta plus 1. Remember, that was my whole goal, was to get the stuff inside the square root to be a tan squared theta plus 1, because at this point we can go ahead and replace that with a secant squared. And once again, you have to think a little bit about the signs here, but the signs work out in this case, because think about the range of arctangent. The secant, which is 1 over cosine, is going to be positive here. So the absolute value of secant is actually just secant here. So this is going to become the integral of, I can cancel off my 2's, and I'm going to have secant squared theta over 4 tan squared theta secant theta d theta. Okay, so this is starting to become a little bit better, because now I can actually cancel off a secant from the top, and I can cancel off a secant from the bottom there. So now we just need to simplify secant theta over tangent theta. And how do we do this? Well, the easiest way to think about this, in my opinion, is to start rewriting this stuff in terms of cosines and sines. This is going to be 1 over cosine theta. And let's bring that 1/4 out front, just so I don't have to keep messing around with it inside with everything else, over sine squared theta over cosine squared theta. So we have a complex fraction in here, but fortunately it simplifies pretty nicely to give me 1/4 integral of, why am I losing things here, cosine theta on top and sine squared theta on the bottom, d theta. Now, at this point, we have to do another substitution, because in order to integrate this, I need to make a u substitution, or that's really definitely the easy way to do this. So what I can do is I can say, let's let u be equal to sine theta, then du is cos theta d theta. So this becomes the integral, well, 1/4 times the integral of du over u squared. That's really u to the minus 2. So this becomes negative 1/4 times 1 over u, which is going, plus a constant of integration. So that is going to be negative 1 over 4 sine theta plus a constant of integration, which is going to be -1/4 cosecant theta plus a constant of integration. Okay, little bit of a mess there, but again, it's lengthy, but really every single step here, if you just take it one step at a time, each step is going to be something we know how to do. And you just have to kind of be willing to try it and see where it goes, and eventually it will get you somewhere, hopefully good. Now we need to go back and we need to figure out what is cosecant theta in terms of x. Well, I'm going to erase this stuff up here, but leave the original substitution so that I've got a bit of space here. You can see these problems are quite lengthy. This is why if you have, you can end up taking up entire roomfuls of boards with these problems sometimes. But what I can do is I want to make a triangle, and I want x over 2 to be the tangent of this angle theta. Well, what is tangent? It's opposite over adjacent. So opposite over adjacent should be x over 2. Let's make the opposite x and the adjacent side length 2. Hopefully you can see why this works. This gives me the correct thing. Now notice, there's alternatives here. I could have said, I'm going to make the opposite x over 2 and the adjacent side 1. That would work as well. I can take my triangle and I can scale it in different ways and still make this thing work out. But let's make things easy on ourselves, not have fractions. We'll make the opposite side x and the adjacent side 2. So now what we're going to do is we just have to figure out what is cosecant theta. Well, cosecant theta is going to be hypotenuse divided by opposite. And you can remember this because, of course, it's the reciprocal of sine. Sine would be opposite over hypotenuse. Taking the reciprocal is hypotenuse over opposite. What is the hypotenuse here? Well, it's the square root of 4 plus x squared. Remember that a 4 plus x squared showed up in our original problem? That is not a coincidence here. That 4 plus x squared being in the original problem, well, I guess I wrote it as x squared plus 4, but same difference. That, sometimes you'll do two different trig substitution problems and they'll give you the same integral even though your original expressions were different. What will end up happening in those cases, though, is that when you write things back in terms of x's, the putting things back in terms of x's will bring back whatever terms you originally had in some form or another. So your final answers will be different for different integrals, even if you solve them by using the same trigonometric integral. So that's something that students have been concerned about to me in the past. They'll be like, well, I've done these two different problems and they give me the same trig integral, but they were different to begin with. That's fine. Sometimes you end up with the same trig integral. It will all go back to normal when we start putting things back in terms of x's. So, where were we? We were writing down cosecant, which was hypotenuse over opposite. What is hypotenuse over opposite? Well, it's just this. Let's just write it down. -1/4, and then we have hypotenuse, square root of 4 plus x squared. All of that is going to be divided by x, and then we have a constant of integration. There we go. We have gotten this trig substitution done. There's one more form of trig substitution that you want to keep in mind. So we've dealt with the sines and cosines identity. This one used the tangent and secant identity. The last form, you might think it's the cosecant and cotangent, and you could do it that way, but actually the last form I want to think about is this. Secant squared theta minus 1 equals tangent squared theta. Is there some way that we can exploit that form of the Pythagorean identity to solve these kinds of problems? Well, the answer is yes. And again, give me a second while I bring up an example of that kind of thing. All right, so I wanted to take a look at one that doesn't actually involve a square root in it. And one of the reasons that I want to do this is because, as we will see, these kinds of integrals kind of crop up naturally in our next section. Because what we're going to do after the trig integrals is we're going to start, after the trig substitution is we're going to start looking at some problems involving what are called partial fraction decomposition, and these kinds of integrals are going to come up naturally, as we will see. So, what are we going to do here? We don't have a square root, but maybe we can use the same kinds of tricks, because unfortunately, this thing being in the denominator, it still kind of creates a mess, and I cannot do any kind of nice ordinary u substitution. But here's what I might be able to do. I can make use of the identity that secant squared theta minus 1 equals tangent squared theta to maybe consolidate this down into a single thing, if only this were x squared minus 1. Well, I can rewrite this as 1/4 times the integral of dx over x over 2 squared minus 1. So I factored a 4 out of the denominator here. Then what I can do is I can say, okay, let's let x over 2 be equal to secant theta. That means that x is equal to 2 secant theta. And this means that dx is going to be equal to 2 secant theta tangent theta, if I'm not mistaken here, right? Because the derivative of secant is tangent times secant, or secant times tangent, as I've written it here. So now what we can do is we can rewrite this as 1/4 times the integral of, I replaced the dx, oh, I'm sorry, I forgot my d theta here. I replaced the dx with this stuff in terms of my thetas, so this is going to be 2 secant theta tangent theta d theta, and this is all going to be divided by secant squared theta minus 1. This, the 2 cancels to give me a 1/2 out front, and this is going to be secant theta tangent theta over tangent squared theta d theta. So my tangents cancel, and I am left with 1/2 integral secant theta over tangent theta d theta. So this is going to be 1/2 integral of 1 over cosine theta times cosine theta over sine theta d theta, and that is going to be the integral of, let's see, this is going to become 1 over sine theta, so that's just going to be cosecant theta d theta. And now we just have to figure out what is the antiderivative of cosecant. Now this is frankly one that you're just going to probably want to remember because it does come up an awful lot. But the antiderivative of cosecant is kind of similar to the antiderivative of secant. And the way that you find it is with a similar multiply by something that is kind of complicated, and it sort of pops out of that. You end up with, this comes out to be, oh, I lost my factor of 1/2, didn't I? This comes out to be negative 1/2 times the natural log of the absolute value of cosecant theta plus cotangent theta plus a constant. And so we end up with this sort of messy thing, and then we have to go back and to rewrite this thing in terms of our original variable x. Sorry, just double checking something before we move on with this. So at this point, we need to rewrite this. Well, how do we do that? The thing is, x over 2 is the secant of theta. I'm going to build a triangle whose secant is x over 2. Well, the secant is 1 over the cosine. 1 over the cosine is hypotenuse over adjacent. So if I make the hypotenuse an x and the adjacent side a 2, that gives me my triangle. Now, that means this opposite side is going to be the square root of x squared minus 4. And take a minute to see if you can figure out how to rewrite this in terms of x's from that. Okay, so were you able to do it? Sorry, let me adjust the camera there a bit. Well, this is going to be negative 1/2 times the log, absolute value. Now the cosecant is going to be the reciprocal of the sine. So it's going to be hypotenuse over opposite. So this is going to be x over square root x squared minus 4. And then the cotangent is the adjacent over the opposite. So this is going to be plus 2 divided by the square root of x squared minus 4. And then we still have the plus c on here. Okay, so that turned out to be surprisingly messy. It really did. It came out to be quite the annoying little thing there. But the point is we were able to do it using this trick. Now, I want to mention actually something else that if this problem had been just slightly different, it would have been way easier. Why? Well, let me show you a slightly different problem. What if this had been x squared plus 4? And this is what I was double checking a moment ago when I paused my recording again, because I was like, I want to make sure that this other thing I want to show them, it really does work out the way that I think. This would be the integral of 1/4 1 over x over 2 squared plus 1 dx. Well, here's the thing. If I do a u substitution of u equals x over 1/2, this becomes 1 over u squared plus 1. But guess what 1 over u squared plus 1 is? That is actually the derivative. I have now lost it here because I had the whole list up. There it is. That is actually the derivative of arctangent. This is the derivative of inverse tangent u. So if you recognize a pattern like this, then you don't need to do a trig substitution in order to get it. You can actually just remember this is a derivative of arctangent, we're all set. But because this was a minus 4, that really threw everything out the window for us, okay? So that really messed everything up. Now you might wonder, is there a way that we could have messed around with things in order to make that work out in terms of arctangents anyway? And the answer is yes. Actually, there is a way that we could have turned that x squared minus 4 into a problem that sort of involves arctangents. However, in order to do it, and if you guys want to stop here, that's fine, but I just want to very quickly mention how you could do it if you had 1 over x squared minus, let's just do minus 1 instead of minus 4 because I don't feel like keeping track of these factors of 1/2 and 1/4 that keep floating around. Let's suppose that I wanted to try to rewrite this using arctangents. Well, here's what I could do. I could try to factor an I out of each of these things. This is actually 1 over negative ix squared minus 1. So this becomes negative 1 over ix squared plus 1. And then what you do is you do a u substitution, u equals ix. And what you end up with is, well, you end up with 1 over u squared plus 1, which comes out to be, when you do the antiderivative, you get an arctangent. But, and here's the key thing, you end up with imaginary numbers in there. But the interesting thing is that this technique should work just as well. There's nothing wrong with this technique. Like what we just did should just work. So, the upshot of all this is that there are some antiderivatives that are actually made easier in some ways if you're allowed to use imaginary numbers or complex numbers in general. The term imaginary numbers, by the way, is a terrible name for them because it implies like real numbers exist and complex numbers don't exist. Well, that's not true. It's just that most things in the real world that we encounter every day are described by real numbers. Like lengths or weights. They're described by real numbers, not complex numbers. But there are things that are described by complex numbers, and from a mathematical perspective, real numbers and complex numbers are both just abstract logical constructions that we use to describe the world. And they describe the world correctly, but they're still just these abstract concepts that we're using. So it's not like one is more real than the other. So the term real versus imaginary is kind of a terrible, terrible naming convention, because it makes you think one is the actual, oh, these are the numbers that exist and those numbers don't exist. Well, no, it's more like real numbers are the things that you can use to describe lengths and weights. Complex numbers don't describe lengths and weights, but they actually do describe other things in the physical world. For example, everything in quantum mechanics has to be described in terms of complex numbers. All right, I'm going to end there. In the next lecture, what we're going to do is we're going to summarize the rules that we saw here, and then we're also going to give a brief discussion of what do you do if you have a definite integral. Now, because this is such a complicated topic, I'm also going to be linking to a discussion from someone else, Krista King's video on YouTube, which a student that I mentored highly recommended Krista King's approach to doing these. So hopefully you'll be able to check that out as well and see another perspective on how to do these problems. But in the meantime, we'll pick back up on this next time.